this lesson we're going to take a look at proving trig identities. So we're going to use a lot of the identities that we've come across in grades 11 and 12 to help us to solve and work through solving identities. Remember, identities, we look at sort of trying to solve left side equals right side. So we're going to take a look at a couple of these examples. Remember, or recall, we have related identities, we have correlated identities, and then we have our main compound angle formulas. Again, these are the ones that help derive our correlated, and we'll do a couple of examples. Make sure you know the reciprocals, and then from grade 11, our two identities, both Pythagorean and quotient. So let's get started. The first identity we're going to derive or prove is something called the double angle formula. It's called the double angle formula because we're multiplying the normal x angle by 2. That's it. So one way to work with identities is pick a side to work with and work as far as you can down. Now normally you would look at the more complex side, and in this case that might look like the right hand side, but there isn't a whole lot we can do with sine and cos. So I am going to start on the left hand side, and the first thing that I'm going to do is I'm going to recognize that sine of 2x can also be rewritten as sine of x plus x. Now this is very helpful because I have a identity here, and I have a compound angle formula which is sine x plus y equals sine x cos y plus cos x sine y, and as long as I have two angles I can expand out sine of one angle plus the other. And so that's the approach we're going to take a look at. So I'm going to take this left hand side and I'm going to expand it by writing it as sine x cos x plus cos x sine x. So remember the expansion. If it's sine, the signs will be the same, and it's sine cos cosine. This is angle 1, angle 2, angle 1, angle 2. Now because they're both x, these are really the same two things. It doesn't matter which order I write these in. So this is sine x cos x plus cos x sine x, which could also be sine x cos x. So really there's two of them. So 1 plus 1 is just simply 2 sine x cos x. And with identities, as soon as we complete one line, we always look up to the side we're trying to solve and make it look like, and we see very quickly we have exactly the double angle identity. So we call it formula or identity, but basically we can now say that sine of 2x is equal to 2 sine x cos x. There's a double angle formula or identity for cos as well, but we'll look at that at a later time. So we would say left side is equal to right side. The second example is one that we've looked at before in our cofunction. And so again, what we want to do is we want to show that cos of pi over 2 minus x is equivalent to sine of x. We did this already when we worked with the values from the unit circle, and we took a look at x, and we also said that the angle could be pi over 2 minus x, which would give us this angle right here, and we developed these correlated identities. Well, we're not going to use that method anymore. What we're going to do is we're going to use the ability to expand cos of, let's call it a minus b. And that expansion looks like this. Cos of a, cos of b. Remember, in the cos expansion, the signs are the opposite. And then we have sine of a, sine of b. Now in my particular example, I have cos of pi over 2 minus x. And so what I'm going to do on the left hand side is I'm going to expand this. So this becomes cos of pi over 2 cos of x plus sine of pi over 2 sine of x. Now I can look at the unit circle and I can find the value of cos of pi over 2. Well, remember from the unit circle, pi over 2 is straight up, and this has the point 0, 1. Well, the cos is always the first value, which is in fact 0, times the cos of x, plus the value of sine, which is the second value, which is 1. So these numbers appear or come from the unit circle. Well, 0 times cos x is 0, and all I'm left with is the sine of x, which is in fact what I wanted on the right hand side. So in both of these examples we use those compound angles, sum and cos. moving to example 3. This one's a little bit more complex. This one involves reciprocals, but we approach it the same way. So remember the steps when you're solving identities. The first one is pick a side that is most complex. And that just allows us to do more with it. Once you've chosen that side, then continue as far down as you can until you get stuck. Then you have an option of working on the other side. The third idea is to rewrite everything in terms of sine and cos. And that's an approach we're going to take. So again, this is a good example. You could start with the right, you could start with the left to see what we're trying to solve for. So if we work with the left hand side, I'm going to change this to 1 over the sine of 2x. And I know from before that I have a double angle that I can rewrite this out. Well, sine of 2x is equivalent to 2 sine x cos x. So I've worked that down a little bit. I can't do too much more with it. So I'm going to stop and I'm going to move over to the other side. And I'm going to say, well, the right hand side is cos secant x, which is the same as 1 over sine of x, all over 2 cos of x. Well, this is really over 1, so I'm going to take this and flip it and multiply to divide by the fraction. So the next line would be 1 over sine of x times 1 over 2 cos of x. And I can see very clearly that when I multiply these together, remember numerator times numerator, denominator times denominator, I in fact have 2 sine x cos x, which is exactly what I had on the left hand side. So this is a good example where we worked down one side until everything was simplified in terms of sine and cos, and then we worked down the left hand side. So now once again, left side is equal to right side. The next example is a little bit more complex, but once again we're just going to break it down and use some of our knowledge from before. So I noticed that cos of x plus y could be expanded using the compound angle. Same thing with cos of x minus y. On the right hand side, I've got some options as well. I could rewrite this cos squared x as 1 minus sine squared x. Remember that from the Pythagorean identity. And I could write cos squared y as 1 minus cos squared y. Oops, sorry, sine. So these are options. One I can't do much with, other than if I really wanted to, and this is a very rare case, but sometimes you could replace 1 with sine squared plus cos squared. Again, that Pythagorean identity. So I'm looking at this and I'm thinking the left hand side looks a little bit more complex. So I'm going to expand each of these independently and see what I get. So cos of x plus y becomes cos of x cos of y minus sine of x sine of y, all in brackets. Then I have cos of x cos of y again. Then I have plus sine of x sine of y. This is all on the left hand side. Now I'm going to take the unusual step of actually making this a little bit more complex, and then I think it's going to simplify. So I am going to multiply, foiling these two binomials out. So I have cos of x cos of y cos of x cos of y. So that becomes cos squared x cos squared y. Then I have cos of xy cos x cos y times sine x sine y, and I have the same thing in here, but look at this. I think they're going to cancel out. So I'm going to expand this, but I'm going to do it in a different color because I think they're going to expand or cancel out. So it's going to be plus, it's going to be sine x sine y cos x cos y minus sine x sine y cos x cos y. And in fact these are identical, so they are going to cancel out. And then I'm finally left with a negative sine squared x sine squared y. These disappear, And on the left hand side I am left with cos squared x, cos squared y, minus sine squared x, sine squared y. So that's all on the left hand side. Now I take a look up, and this doesn't quite look like what I have on the right hand side. So I've got a cos squared x and I've got a cos squared y, but I notice everything's in terms of cos. So maybe that's a good idea. Maybe what I should do is I should take these sine squareds and write them out as 1 minus cos squared. Let's see what happens when we do that. So I have cos squared x, cos squared y, minus, here's my brackets now, 1 minus cos squared x, this is Pythagorean identity, and 1 minus cos squared y. I'm going to take that extra step of algebra and FOIL those two out, and I'm left with 1 times 1 is 1. Then I have minus cos squared y minus cos squared x, and then I have minus minus, which is a positive, cos squared x, cos squared y. Now I'm starting to see something. I've got a cos squared x and a cos squared y, and if I run that minus sign through, look what happens. This is exactly the same as that, except one is positive and this one will be negative. So once I run this minus sign through, this is going to cancel and this is going to cancel. So let's run this minus sign through. So I have negative 1 plus cos squared y plus cos squared x. Take a look up on the right hand side, and even though it's not written in the same order, is that not the same thing as what I have on the right hand side? Cos squared x plus cos squared y minus 1. And I have the minus 1 up front here, but I can very easily rearrange these and see very quickly that left side is in fact equal to right side. So a little bit more work involved, but again, if I'm careful and I recognize that sometimes you have to blow things up or expand them to simplify them, I just keep working. And that's the nice part about identities. I might not think I'm on the right track, and then all of a sudden, like in the last step, it reveals itself. Okay, there's your homework. We will have another lesson, video review, so please make sure you look for that in the upcoming day or two.